Before electronics, there was control, the world that needed regulation. In the modern world, stability feels inseparable from electronics. Screens monitor everything. Sensors measure every fluctuation. Software reacts in milliseconds. It is easy to believe that without digital feedback, complex systems would collapse into chaos. But the 19th century tells a different story. Long before transistors, before control circuits, before even reliable electricity, entire industries ran with astonishing stability. Hundreds of machines worked simultaneously. Loads changed constantly. Workers engaged and disengaged equipment without warning. Yet speed remained steady. Power stayed balanced. Disasters were rare when systems were properly designed. This was not luck. And it was not brute force. It was control. Victorian engineers understood something fundamental. Regulation does not require intelligence, it requires feedback. And feedback exists everywhere in physics. Gravity, pressure, heat, inertia, centrifugal force, expansion, compression. They learned how to convert those forces into automatic responses. A mill engine powering hundreds of looms could not afford to surge or stall. A boiler could not wait for human judgment when pressure climbed too high. An elevator could not depend on hope if a cable snapped. A train could not rely on perfect behavior across dozens of coupled cars. The systems had to correct themselves. So engineers built machines that felt their own state. Machines where the thing being controlled provided the energy to control itself. Speed produced force. Pressure produced motion. Heat produced bending. Failure produced safety. This is the story of how they did it, not through speculation or lost technology, but through mechanisms that still exist, still work, and can still be observed in museums and preserved installations today. The first of these mechanisms became the symbol of the entire industrial age. The spinning arms that ruled industry, speed regulation without sensors. The heart of industrial stability was speed. If a steam engine ran too fast, machines shattered. If it slowed, production collapsed. Load changed constantly as workers engaged and disengaged equipment. Human reaction was too slow. Something had to respond instantly. The solution came in the form of the centrifugal governor, perfected by James Watt in 1788. The principle was disarmingly simple: 0.2 metal balls mounted on arms rotated with the engine shaft. As speed increased, centrifugal force pushed the balls outward and upward. This movement was transferred through levers to a valve controlling steam flow. Faster speed reduced steam. Slower speed increased no measurements. No decisions. No external power. The deviation itself created the correction. This was a pure mechanical negative feedback loop, the same concept that underlies modern control theory, implemented with gravity and motion instead of electronics. Properly tuned governors maintain speed within roughly 2%, even under load changes exceeding 50%. That level of accuracy was more than sufficient for looms, pumps, generators, and mills. The 1876 Philadelphia Centennial Exposition. A single massive engine controlled by a centrifugal governor powered the entire industrial hall, over 1,400 horsepower, with machines switching on and off all day. Observers recorded speed variation of only a few dozen revolutions around the target. This mechanism spread everywhere. Textile mills, municipal water systems, early electrical generators. Even today, small hydroelectric plants still rely on mechanical governors because they are simple, robust, and immune to electrical failure. But speed was only one danger. Pressure was far more unforgiving. When physics decides not people, pressure, gravity, and absolute limits, steam boilers were the beating hearts of industry, and the most dangerous machines of the age. Pressure stored enormous energy. Exceeds safe limits, and the result was catastrophic explosion. No human reaction time could prevent it. Control had to be automatic. The answer was the weight-loaded safety valve. A metal disc sealed an opening in the boiler. A known weight pressed it closed. When pressure exceeded the force of that weight, the valve lifted. Steam escaped. Pressure dropped. The valve receded. No detection. No judgment. Just force balancing force. Pressure at opening was determined by a simple equation. Force divided by area equals pressure. To adjust the limit, engineers adjusted weight or lever geometry. Multiple valves were installed at increasing thresholds to create redundancy. If one failed, another would open. Insurance records from the late 19th century show a stark truth. Boiler explosions almost always occurred when safety valves were tampered with. When left alone, they worked. This principle survives today. Modern pressure vessels still rely on mechanical relief valves as the final line of defense. Electronics may monitor, but physics still decides. The same philosophy saved lives in a far more dramatic context. The moment elevators became safe, fail-safe design in motion, early elevators terrified the public for good reason. A snapped cable meant death. In 1852, Elisha Otis introduced a solution that changed cities forever. His governor detected excessive speed, not failure. As an elevator descended, a pulley rotated. Weights mounted on it responded to speed. If descent accelerated beyond safe limits, centrifugal force threw the weights outward, triggering springs that slammed brake shoes into guide rails. The faster it fell, the harder it stopped. The system required no power. The dangerous condition activated the protection. And crucially, it failed safely. If anything broke, brakes engaged. Otis proved it publicly in 1854 by cutting the supporting rope during a live demonstration. The platform dropped inches, then stopped dead. Skyscrapers followed. This principle, failure causing safety not danger, became a defining rule of mechanical regulation. It reappeared everywhere, including in systems distributing power itself. Stability at city scale, water, electricity, and massive inertia. As power systems grew, regulation had to scale. Hydroelectric plants faced constant load changes. Electrical frequency demanded precision. The solution combined old ideas with new scale. At Niagara Falls in 1895, turbines used centrifugal governors linked to hydraulic servos. Small speed changes moved pilot valves. Pressurized oil amplified motion to massive water gates. To prevent oscillation, engineers added dashpots, viscous dampers that resisted sudden movement. This stabilized response without slowing necessary correction. The result? Speed regulation within plus or minus 0.5% under full load variation. Meanwhile, cities like London ran entire hydraulic power networks using gravitational accumulators. Massive pistons weighing hundreds of tons created constant pressure purely through gravity. Demand fluctuated wildly, pressure did not. When demand rose, pistons descended. When pumps exceeded demand, pistons rose. Pressure stayed constant because weight never changed. These accumulators operated for nearly a century. No sensors. No controllers. Just mass and area. But safety in motion required more than pressure and speed. Trains introduced a new kind of risk. Failing safely every time, brakes, heat, and coordinated control. Railways demanded absolute reliability. In 1869, George Westinghouse solved braking by reversing logic. His air brake system applied brakes when pressure was lost, not applied. A broken hose meant full braking instantly. Every car responded simultaneously. Failure produced safety. The same thinking governed temperature regulation. Bimetallic thermostats use differential expansion to switch heat on and off automatically. No calibration drift. No power requirement. Some operated for 70 years without replacement. Finally, complex linkage systems coordinated multiple actions from single inputs, throttles, valves, timing, using geometry instead of computation. Mechanical systems enforce correct relationships physically. By the time electronics arrived, the principles were already mature. Control did not begin with computers. These systems prove a simple truth. Regulation is not digital. It is physical. Electronics refined control, they did not invent it. Victorian engineers solved stability using immutable forces that still govern reality today. When you understand that, history stops looking primitive and starts looking brilliant. If this kind of grounded engineering history matters to you, support it. These mechanisms still exist. They still work. And they still have something to teach us. See you in the next exploration of how physics, not speculation, shape the world.